Advanced Material Chemistry Course Coordinator Dr. Vinita Grover Gupta, Teaching Faculties of Advanced Material Chemistry Course Dr. Dimple Datta, actually she is absent, Dr. Sanjukta Avai Kumar, Dr. Sashwati Sen, and Dr. Kanchan Bari, all DAE and non-DAE participants of this course. A very good afternoon to you all and warm welcome to the inaugural session of the HBNI Advanced Material Chemistry Course 2025. It gives me immense pleasure to share this year that this year we are having nearly 93 number of enrollment for this course, and out of this, nearly 15 participants are from non-DAE. This is a huge leap compared to the last year enrollment. So before proceeding to the lectures of this course, it is necessary for all of you to know about HBNI, a deemed to be university, where you people have enrolled. For this, now I request Dr. A.K. Tyagi to give an overview of HBNI and also may add the inception of this course for you all.
Thanks, Dr. Madhumita. First of all, let me also welcome all the faculty members who are sitting in person and our participants, except one, all of them are online. So, warm welcome to this program, nice course which we have conceived for the benefit of students from all over India. As you know, this course is being offered under the auspices of Homi Bhabha National Institute. Many of you may not be knowing what this institute is all about because it is not very old. So, the genesis of HBNI started sometime in the year 2001 or so. Dr. Anil Kakodkar, then Chairman Atomic Energy Commission, as Secretary of Department of Atomic Energy, it was his brainchild. Along with him, we had Professor R.B. Grover. These two, I can say, are the pillars of Homi Bhabha National Institute, in short, HBNI. So, first 2-3 years, of course, a lot of efforts were made formally and informally. Finally, it was June 3rd, 2005, when Government of India declared HBNI as deemed to be university under Section 3 of UGC Act 1956. So in this act, there is a provision of declaring important institutions as deemed to be university. It was 2014 when HBNI became a granting aid of institution. Many non-DAE participants would be wondering that in Department of Atomic Energy, which is a mission mode organization, what is the role of an educational institution like HBNI? You are correct in your thinking. Anyone would think like this. Let me begin with DAE. DAE was founded way back in 1954, to be very precise, on 3rd of August 1954, by a great son of India, Dr. Homi Jahangir Bhabha, whom we lost untimely on 24th of January 1966 in a plane crash. All these things are very well documented, so hence I want to spend much time on this. So DAE can be divided into several types of organization. First set of organization is R&D units. Here we have got Bhabha Atomic Research Center, BARC, which is at Trombay, mainly at Trombay. Of course, it has its footprint in other parts of country also. Then we have got Indira Gandhi Center for Atomic Research. It is in Kalpakkam, close to Chennai. We have Raja Ramanna Center for Advanced Technologies in Indore. RRCAT came into existence in 1984 and IGCAR came into existence in 1971. It was called as that time RRC, Research Reactor Center. Then we have got VECC, Variable Energy Cyclotron, came into existence in 1970s. This is in Kolkata. And AMDER headquarters is in Hyderabad. GCNEP is situated at Bahadurgarh, near New Delhi. So these are the 6 R&D centers. Then other class of institutions in DAE is PSUs. We have got public sector units such as NPCIL, Nuclear Power Corporation of India Limited, the organization responsible for nuclear power in our country. We have got other PSUs also. Then, of course, we have got industry and mineral sector. Here we have got AMDER. AMD, of course, is part of R&D as well. We have got BRIT, for example, it is industrial unit. High Water Board is also industrial unit. UCIL is a PSU, so is ECIL. These are PSUs. We have 3 PSUs. Fourth category is service-based organizations. We have GSO in Kalpakam and DCSEM in Mumbai. Fifth important category is granting aid institutions, the institutions which get aid from DAE, and we have got 11 of them. TIFR is the oldest unit of DAE. TIFR was founded, to be very precise, on 1st June 1945, that is before independence. You can imagine Dr. Bhaba's vision. Even before India got independence, he was thinking about atomic energy program and so on. And HBNI is one of the 11 aided institutions of DAE. As I mentioned, it became granting an institution of DAE in 2014. In 2016, it was CEBS, the youngest AI of DAE. In 2016, they became part of DAE as granting aid institution. This was about DAE in general, in particular for the benefit of non-DAE participants. I can see a number of them are there. Now coming to SBNI, after SBNI was founded on June 3rd, 2005, since then we celebrate June 3rd as the foundation day of SBNI. Every year we are celebrating. We began with 10 institutions. SBNI is the academic wing of DAE. If you ask me one sentence to describe DAE, where SBNI is placed in DAE and what is its main function, I would say Homi Bhabha National Institute is the academic wing of DAE. Idea of Dr. Kakodkar was that we have got several institutions in DAE, how to bring synergy among them, how to have formal collaborations. Earlier we used to have a lot of collaborations, rather informally, on one-to-one basis. But with the advent of HBNI, now we have got very formal collaborations. So to begin with, we had 10 CIs. CI is called as Constituent Institution. All these 4 R&D units, and there were 6 of aided institutions, which became part of HBNI way back in 2005 itself. Subsequently, NISA Bhubaneswar joined us, and in recent time, in last about 1.5 years, 2 more institutions of DAE have joined HBNI for its academic program. We follow federal structure. We are in central office, and these institutions are all over India. So not that they are linked with us in terms of administration, they are linked with us in terms of academic programs. So these 2 new institutions are Homi Bhabha Cancer Hospital at Varanasi and Homi Bhabha Cancer Hospital and Research Center at New Chandigarh. And some more institutions are going to become part of HBNI. One of them is AMDER Hyderabad. It has got permissions from the highest bodies of HBNI. Now application is in the process of submission to UGC. Then ECTRAC Navi Mumbai, which was part of HBNI, because ECTRAC was a part of TMC, Tata Memorial Center. So now ECTRAC has grown considerably, and very soon ECTRAC also is going to be recognized by UGC as a separate OCC. When I say OCC, it means off-campus center. These terminologies you may not be used to, many of you. How we began our academic program? Like any young university, in 2007, we declared only 2 results. And last year we declared 800 plus results. This all has happened in 20 years. As of now, HBNI has got slightly more than 1250 faculty members. Very large strength is there with us. And we have got slightly more than 3,850. To be very precise, as on last month, it was 3,857 students. So it is a reasonably large size university in terms of faculty members, in terms of students also. What do we offer? We are not a UG university. We are a research university. Please remember that we are not a regular university where you have got thousands of students carrying bags and attending classes of BSc and all that. We are a research university. So mainly we offer PG programs, and above PG, of course, we have got PhD programs. MTech program is being offered by us, and we also offer some of the super specialty doctor program. For example, DM, MD, MCH, MSc Oncology, and so on, MSc Nursing. These are the important programs which we offer. So as I mentioned, total we are offering 48 programs as of now. A number of programs is going to touch 50 in next few months or so. So in terms of variety of programs, I think we are next to none. Now coming back to some other statistics, so far SBN has declared more than 9,500 results. As I mentioned, 800 were there in last academic year itself. Out of these 9,500 plus results, close to 4,000, to very precise, 3,800 something are PhDs. 1,250 are MTechs. 1,700 plus are high-level medical degrees, in particular in oncologies. So this is a contribution of SBNI towards higher education in this country, and DA in particular. We are proud to say that as on today, as of now, about 10% cancer patients are treated in Tata Memorial Centers, which is part of DA. So you can imagine the impact of TMC in particular, DA in general, TMC in particular, on cancer care in this country. And you know, very recently, Director General of IAEA was in TMC, along with Chairman of Atomic Energy Commission. IAEA has been declared as Ray of Hope Center globally. So it is going to provide cancer care to many, many countries, not only in Asia, Pan-Asia also. We'll also go to Africa and all that. Already a lot of services are being provided. And TMC also has been declared as a nodal agency for BIMSTEC nations. These nations are mainly in South Asia and Southeast Asia, East Asia. So this is the role of DA in general, as I mentioned, and SBNI in particular. SBNI acts a sort of catalyst to all these high-end programs. Where we stand compared to our peers in India. I may quote latest NIRF results, which were declared a couple of months back. I am very proud to say that a young university like SBNI, which is just about 20 years old, this year we have secured 7th rank in India among research universities and 12th rank overall, 12th rank among universities and 20th rank overall. All the institutions put together, we are 20th, which is no mean achievement for a young university like us. And of course, the credit of this goes to our large number of faculty members and our large number of students spread over these 13 institutions. Nature Index has rated SBNI at the first position in journals of physical sciences. And as far as overall rating is concerned, we hop between second and third. Sometimes we are second, sometimes we are third. Even if we are third, it is a very respectable number. Anyone who is among first three should be proud of. So this is the impact of SBNI in higher education scenario of this country. We do many other things also for the benefit of the students who come from remote areas as part of NEP 2020. NEP, as you know, was introduced in 2020. It has got several mandates. Many of them we are fulfilling and we are progressing further. One mandate is to provide high quality courses to students, not only belonging to our university, but also to people, young students from remote areas. In this process, we are also in the process of, in this direction, we are also in the process of initiating courses in local languages. So one course in Marathi is in advanced stage of conception, and I'm sure we are going to record it very soon. Likewise, we have in pipeline courses in other languages also, Bengali and so on. And we also help people from vernacular medium by way of publishing nuclear glossaries. Already in Hindi medium, Hindi glossary has been published about 3 years ago. Presently, we are working on 4 glossaries parallelly. They are Marathi, Gujarati, Bengali, and Tamil. And after these glossaries are over, we are going to initiate work on 4 more new glossaries. So as part of our mandate and as part of our commitment towards young students, we have come up with several high-end courses. It is not possible for many universities to offer the kind of skills which one needs to come up with this kind of courses. Fortunately, we being in DAE, we have got large number of faculty members who themselves are top class researchers who have spent decades in a given field. And with their help, we have come up with number of courses, high-end courses. Some of them are on NPTEL also. One of the courses on introduction of lasers has been taken recently by 1,600 plus students from all over India. So one such course is Advanced Materials Chemistry course. This course contained, you all have seen, it was advertised very well by our colleagues here in Central Office of HBNI. This course we initiated in 2020. So this is the 4th edition of this course. I know some of the faculty members are there right from beginning in this course. Dr. Dimple Datta, Dr. Vinita. I myself used to take classes till last year, but now I have become a bit busy. So I have, not that I don't like to take classes, I like to take classes, but maybe I will come up with some other course. This course now is being spearheaded by younger colleagues. So this is a 4th edition, and you will see this course is very balanced. We took a couple of months to formulate the syllabus of this course. It is not the syllabus was formulated just in a matter of 10 days or so. We took decent time. We took inputs from large number of stakeholders, what they want, and based on that, this course was curated. And we have got, as I mentioned, highly experienced faculty members. And I'm sure that you all will find this course useful. This is a 3-credit course as per new uniform credit structure of UGC. And please be attentive, ask questions to the faculty members, and you can ask questions by email also, if suppose time does not permit to ask question on the spot. These are the courses which are called as interactive courses in terms of UGC language. It means they are equivalent to classroom courses. So interactive course means the course where participants can ask a question or two during the lecture. So it is just like a course which you take in physical mode by attending classrooms. It is more or less that only. And make notes. I will always recommend that to young students. Making notes is a good habit. And please be assured that whatever time you are going to spend on this course, it is going to fetch you rich returns. With this, I conclude my address. Thank you very much, and let me welcome you all once again.
Thank you very much, sir, for such an excellent briefing about DAE and setting up all the DAE units, including RAD units, PSC units, their granting ed units, and also giving the overview of HBNI and its all CI and OCG. Thank you very much for enlightening us about the mandate, activity, and programs of the HBNI. And we are all thankful for the inception of this advanced material course. So now I will just give the technical details of this advanced material course. So as you know that this course consists of 45 lectures, 45 hours lectures, which will be of 3 credits. And these 45 lectures will be covered in 30 sessions, and each session will be 1.5 hours duration. So total, this course consists of 5 modules, and this will cover on general chemistry, characterization technique, traces and alter traces analysis, and functional material part 1 and part 2. And these modules will be offered by 5 experts from respective fields from BARC. These lectures will be delivered in online mode, and this is in a hybrid mode, so using WebEx platform, and this will be also available on YouTube. So please join the classes using the link which has been shared by the IT teams. Regarding the credit of the course, there will be regular assignment and examination. The student who wants to earn the credits for this course has to complete the assignment and examination. To earn credit, the participant must have the attendance of minimum 55% lectures and clear all the examination with more than 50% of overall marks. Those who do not take assignment or an exams and meet the attendance of 75%, they can be given the participation certificate by HBNI. So please mark your attendance in each class. Please join the class within the 15 minutes of the starting of the class. If you have any doubts, please ask, because these classes are online interactive mode class. For non-DA participants, if you want credits, you need to pay extra 1,000 rupees for assignments. So these are all the technical details from my side. Now I will request Dr. Vinita Grover Gupta to give more details about the course content and also introduce the lecturers of this module of this courses. Thank you.
Not this one,
Yeah,
the other one.
first, not this one. Or this one I had sent. I had sent files, no?
Okay.
This is the first lecture.
This is the first.
Yeah, this one. Yeah. Let's hear this one.
I shared the
Okay.
AMC note. Anyway, I'll not use. Okay. So good afternoon, everybody. And I welcome you again for the Advanced Material Chemistry course that would happen over next 3 months, a little over 3 months, of course. And time slot, as you all know, would be 2:30 to 4 o'clock. I was supposed to have a PPT with me here, but anyway, I think it's a good way to talk to everybody one-on-one. So, at the outset, why advanced material chemistry? Why do we need materials at all? So, all of us know that materials are important for the advancement of society. And advancement of society critically depends upon materials. So, it's to and fro traffic that we work on. There was one said that probably without man, materials can exist, but without materials, the mankind and society cannot exist. All of us have studied in the primary and middle classes about the prehistoric ages, and materials are so important that actually the prehistoric ages were also named after the kind of the material that was used and employed by the whatever form of human was existing in that particular age, right from Stone Age to Bronze Age. We then ushered into Silicon Age, and now we are going towards the Nano Age. That is, all of us are aware of it. So we started with the natural materials, which is wood, stone, etc. And then we went on to plastics and composites, which is the backbone of today's infrastructural material. And slowly and steadily, we are moving towards the smart adaptive material. Now, these are the material that actually recognize the external stimuli and then act on it. This is how the society is working. So, just to put a context, why do we need to study materials chemistry in the contemporary time? Even United Nations has understood. United Nations actually, if you all of you are aware of it, has coined 17 Sustainable Development Goal. And yesterday evening, I was going through all of them and I realized that if not all, at least 7 to 10 goals are directly correlated with cost-effective advanced material which are made from naturally abundant resources. So such is the importance of material, and there is a requirement of to satisfy these sustainable development goal. There is a requirement of advanced material for healthcare, for energy, for catalysis, for getting good hydrogen chemistry, hydrogen economy that we are working on. So, which now this means that the research on materials is very important in contemporary times, considering the requirement. If a scientist or a technologist, let's say, want to do a research on materials chemistry, on an average, what would he do? First, it would start with a proper choice of material, the application that he is looking at, it would involve synthesis of the material. Then he would go on to characterizing it, whether he has achieved that material or not. Then parallelly or sequentially, he would want to do the compositional analysis. Subsequently, he would want to do the property evaluation, whether whatever property he had thought this material would possess, whether it possesses it or not. And lastly, if the material satisfy all the criteria, he would want to go into the device fabrication. I mean, this is the natural progression of things that we suppose would happen for a scientist or a technologist. Now, if you look at this advanced material chemistry course, this is exactly conceptualized keeping these 5 stages in mind. So the first part is the general materials chemistry, which would talk about crystal structure, property, how the composition and structure are related to property, how the defects would lead to the properties and so on, and of course the synthesis of material. This would be followed by second module, which contains the characterization technique, following which you'll have a module on compositional analysis, and then there'll be 2 modules on functional material, the first one of which will majorly deal with magnetic and energy material, and the last one would deal with mostly the device-worthy material, which would include thermoelectric, photovoltaics, and so on. So this is the kind of overview that I wanted to give. Now, I think now is a good time to introduce, okay, now we have PPT. Maybe we can scroll further. The right time we have got the PPT, because this is the time to introduce our faculty for this particular course. Next slide, please. Next, yeah, just the previous slide. Okay. So as I said, there are 5 modules. I would take the first one. And each session is 1.5 lectures, which is 90 minutes. Professor Kanu Barik would take characterization technique. Professor Sanjukta would be teaching you about different analytical techniques on all the scales, major trace, ultra trace. Professor Dimple Datta would be talking to you about the important functional materials. And then Professor Shashwati would take you forward in the device-worthy material. So please, the next slide, please. I would this is my portion that I would be taking. As I just said, it will deal with the basic concept, crystal structure, structure property correlation, defect, solid solution, metastable phases, ultimately leading towards a synthesis of material. So I now request Professor Kanu Barik to introduce himself as well as the portion that he would be taking for you. Next slide, please. Okay. Yeah.
Good afternoon.
Just
Previous slide.
okay.
Yeah, I'm Dr. K. Kanhu Baik. I am from Chemistry Division. So I will mainly cover that second module of this course, that is characterization techniques. As Madam has already discussed what is the importance of this course, and for any material you develop after synthesis, you need proper characterization. You have to see the phase formation, then structural or its microstructural analysis, surface characterization. So in this part, I will mainly cover about how the matter interact with different radiation. Mainly, I will cover X-ray techniques, neutron techniques, these 2 techniques, and electron microscopes. So here I will cover mainly X-ray diffraction analysis and different subsets of X-ray diffraction like thin film XRD, then this is single crystal XRD, synchrotron XRD, and And then I'll go for the scattering techniques, where I'll cover that small angle X-ray scattering and neutron scattering. In addition, also neutron diffraction techniques. And then finally, I'll see some of the electron microscope techniques, where mainly scanning electron microscope, SEM, and transmission electron microscope, TEM, these two thoroughly we'll discuss. And finally, the surface characterization techniques, basically X-ray photoelectron electron spectroscopy or J electron spectroscopy and secondary and mass spectroscopy. So these three surface techniques will be discussed in broadly. Now,
Professor Sanjukta.
Very good afternoon to all the students. So I am Sanjukta A. Kumar from Analytical Chemistry Division, and I will be dealing with the basic concepts and various terminologies used in analytical chemistry. And then from percentage level analysis to sub-PPT and PPT level of analysis of any composition of that material. Like a material is made up of various elements ultimately. And if whether a material will be used for its intended purpose can only be ascertained by analysis of its various elements, whether they are present as per their expectation or expectation of our intended material. So to know that, we have to use various classical techniques as well as analytical techniques to find quantitatively the various elements present in the material. So starting from classical chemistry like gravimetry, volumetry, or calorimetry, which is used for percentage level analysis, slowly we will be moving towards instrumental analysis, which can go to PPP, sub-PPP, or PPT level of analysis. And then sometimes, because when you are doing some PPT level of analysis, it is very much required that you have to separate the metrics, because sometimes the measure metrics may interfere in your analysis. And so we will be looking into the various separation techniques like solvent extraction or ion exchange, how to use that to separate the metrics so that you can get your analyte and you can analyze those analyte using some instrumental technique without interferences. So all these things will be covered in the 9 hours lecture, which is divided into 6 lectures, so 1.5 hours each. Thank you.
Professor Dimple Datta, please.
Very good afternoon. A very good afternoon to all the participants of the course. So I'm Dr. Dimple Datta, and I'm from the Knowledge Management Group, BRC. And as you see, I will be talking to you and discussing with you about functional materials. So once we have learned the general idea of materials chemistry, you have done the characterization and also the trace analysis. So we'll come and discuss about the functional part of these different materials. So where I will be covering mostly magnetic materials, so their concepts, applications, and I'll also be covering multiferroids, GMR, CMR materials. Then a portion of the lecture will be covered on energy storage materials. So where I'll be talking mostly on batteries, which is lithium-ion batteries. I'll be talking about cell characterization, how you have these large-scale applications of energy versus power density, what is the role of energy density in any material when you're looking into energy storage or power density. Then I'll talk about different types of supercapacitors, the different grading of the supercapacitors which we are having. Then we'll talk about components of supercapacitors. So generally we'll talk mostly about all these electrochemical energy storage technologies available. And last lecture, that will be one lecture which I'll be talking about materials for heterogeneous catalysis. So we'll have the basic principles of catalysis. We'll gradually build up. We'll talk about photocatalysis. We'll talk about photoelectrocatalysis, then electrocatalysis. And this is the way we will be covering a portion of the functional materials. And this entire thing will be covered in 5 lectures of 90 minutes each.
Professor Shashwati.
Hello everyone, I'm Shashwati. I'm in the physics group of PRC. So for my part, I will be mainly focusing on the device working materials and the devices which I will be covering is in continuation with energy storage and all. So I will be talking about the photovoltaics, the fundamental, how the light is converted into electricity and how the solar cells work, then the new kind of solar cells like synthesized and perovskite solar cells. Then we will be going to the thermoelectric materials. For thermoelectric materials, what is the basic properties like Seebeck effect, Thomson effect, and then the kind of material which is required, how it can be tailored, how a given material can be tailored for making it into a good thermoelectric material. And finally, I will be talking about important elemental and compound semiconductors and give more emphasis on the silicon and germanium, how the single crystal of silicon is made and thin film propagation techniques, CVD, MV techniques for AMP 2D and 3D printing, with the overview of how they can be used for the production of devices. So that will be the overall.
Not able to. So you have probably.
Next.
Okay. So that was a bird's eye view of the course that would happen over next 3 months. It gives me immense pleasure to share that all 5 of our faculty, they are accomplished scientists, wonderful teachers, and with such competent faculty, an excellent platform of HPNI, and I'm sure very enthusiastic participants. I'm really looking forward to a wonderful 4th edition of AMC course. So thank you very much, and handing back to Professor Madhumita.
Thank you very much, Professor Vinita, for giving such a nice briefing about the course content and also introducing the lecturers. And thank you to all the lecturers of this course who have given the briefing that their course content. And now, actually, it's my pleasure duty to give the vote of thanks to all those who are involved in the program. So first of all, I would like to sincerely thank Professor A.K. Tyagi for his constant support and guidance for conducting this course from HBNA in due time. Its suggestion, every aspect had helped me to formulate and successfully conduct this program. I am very much thankful to Dr. Vinita, the course director, for helping me in each step of coordinating this course. And also she has helped me right from preparing the brochure, releasing the announcement, finalizing the lecture schedules, interacting with the lecturers, and many more works related to this course. Thank you very much, Dr. Vinita. Thanks to all the lecturers, Dr. Dimple Datta, Dr. Sanjukta, Dr. Sasuti, Dr. Vinita, and Dr. Kanucharan Bari for sparing their valuable times and taking the classes and assignments for exams for this course. Actually, they are the backbone of this course, so special thanks to all these lecturers. Now, my sincere thanks to APO HP9, who has agreed to providing the transport for the lecturers for taking this class at the venue. Last but not least, special thanks to HBNA IT team who are actively involved right from the beginning of this program, putting the circular in the on with the website, opening of the registration, contacting the students, sharing the links, and finally they will be recording the lectures on each session. So thank you all for your kind support. Now thank you to all the participants who have enrolled for this course. Please share your feedback about this course, which will help us for further finding the syllabus. Welcome to all of you this first day of the course and wish you all the best. Thank you very much. So now I request all the participants to be with Dr. Vinita for the first lectures and other.
Excuse me, ma'am.
Please
Somebody-
bear
Hello.
with us. Hello.
Ma'am,
Any question?
I have 3 questions.
Okay,
Uh,
please.
The first question is that since the course was postponed by about a month, will and the course completion date is after the new year, and many of the scholars will be, they would have gone to home during the time that the course would end. Would exam date lie in between that or after the course has ended?
See, the exam assignments, I'll tell you, the evaluation process goes like this. Every lecturer, once they finish their module, they'll send you an assignment through course coordinator. Okay, you'll receive the assignment and you'll be given a few number of days, let's say a week or so, to finish that and submit it back. That is the first course of evaluation. So 5 assignments and all. After that, once your course is over, there'll be a break of 15 to 20 days, and the final assessment would be online Viva. That would be conducted right here in HPNI Council Hall. And depending on if you are a Mumbai-based person and want to attend it offline, you're most welcome to do so. Otherwise, the Viva can be conducted online as well. So this is the entire process, how the evaluation goes on. I hope
Okay,
it's
ma'am.
clear.
Yeah, the first question is clear. My second question is, you mentioned that the recordings will be done for all the classes.
Hmm.
Will the recordings be immediately available after the class ends along with the slides, or will there be some kind of delay?
So I think our IT team takes a day to upload the PPTs. So you should get it probably within 24 hours or so.
Will the slides that are being used
Yeah, the
during
slides
the
also
course?
would be available because as you will see as we proceed on with the first lecture today, you will realize that most of the time you see the slides only. Okay. So when the lecture recording is done, it's mostly the slides. You will not get the PPT as such. You will get the lecture recording that consists of slides.
YouTube only. That will be available in YouTube.
It will be available in YouTube also.
Okay, and my final question is, how is emailing the only medium of contact with the instructors, or can more informal means like WhatsApp or other can be utilized after
Okay,
the course
so
hours?
first informal thing is this is an interactive course, so you're welcome to interact with us in the chat box or the way you're doing now. So I think that's the most informal way to go. But second, we would prefer email because depending on the lecturer, these people are not the full-time lecturers, so they are involved in other duties, so they might not be available on phone all the time. And if you are from DA, you realize we do not carry our mobiles inside. So that's the biggest hindrance. So we would prefer email. We would prefer live questions during the interaction session that is going on. However, if something is very pressing, you may mail the concerned faculty, take permission, take appointment, and then if on mutual convenience, you can interact by phone call or I think phone call. Yes.
Okay, thank you.
Okay. Any other queries? Okay, if not, then maybe we break for just 2 minutes and then we start with the first lecture. Thank you very much. So good afternoon again, and now we formally begin our advanced material chemistry course. So I hope all of you are doing well, and I'm really looking forward to interacting with all of you in this particular module, which is the general materials chemistry. Okay, so this module, as I just briefed few minutes back, will consist of more or less the basics. So especially the first lecture, if not other, many of you might be acquainted with, because I will start with the real stepping stone so that we can build up on the basics and take you to little more complex thing that you might or might not have studied. And I would really love to get your feedback. Any questions that you want, please put it in the chat box as and when you want. And every class, today of course we have only 35 to 40 minutes of class left. But in the 1.5 hour lectures that we will have next time onwards, we'll take a break of 5 to 7 minutes, 3 to 4 times to address to your queries and whatever you want to ask, of course, pertaining to this course. Okay, so the first slide. Okay, I'll conclude it. So basically, when we say materials chemistry, material science, what is a material? We know that's a very question, simple question that we ask to a student. It's a substance or a mixture of substance that we call an object. Eventually, what is material science? It is a study of properties of solid material and how material's composition and its structure affect those properties. So when we talk of material, again, we know we talk of crystalline materials and we talk of amorphous material. So what are crystalline materials? Crystalline materials, they have got three-dimensional long-range ordering and periodicity in their atoms, ions, or molecule, whatever is the constituting unit. So there is a regular repeating pattern. It is as if when you walk into the room and you have a tiled surface, the tiles have a regular repeating arrangement. This is somewhat how the crystalline material look like. So examples are the table salt that you use at home. It's one of the most crystalline material known. Diamond, and anything basically. A metal, for example, iron. What is amorphous material? Exactly opposite. They lack any long-range periodic arrangement, and the periodicity, even if it exists, it is only for 2 to 3 units. Let's say 2 to 3 polyhedra. And it won't be more than that, so that you are not able to establish any long-range three-dimensional periodicity. That is what we call as amorphicity or amorphous materials. Okay. Your examples are glasses. That is the most common amorphous material that you encounter. Plastics, gels. So if crystalline solids are at one end of the spectrum, amorphous solid are at the other end. And you know the beauty of it? We all talk about nanomaterial, nanoproducts, nanosolids, etc. Nano is nothing but a state that is intermediate to crystalline solids and amorphous material. How? Your crystalline solids have got long range three-dimensional periodicity. Amorphous, we say, absolutely has no periodicity. Now, nanomaterials have got such small dimension that even though it has three-dimensional periodicity because it is crystalline, but it is so small that the periodicity does not really extend beyond a certain number of planes or certain number of periodic units. So that is how we say that nanomaterials are somewhere between the crystalline solid and amorphous solid. Now, since we are building up the basics and the fundamentals, if I say a crystalline solid, how can I represent it? So crystalline solid can be represented by a smallest unit, which is called the unit cell. And if I ask you to define what is a unit cell, it is the smallest repeating unit that describes the full symmetry of crystal structure. In a simple way, if you look at three patterns that I have copied on, I've drawn on the top of the slide. So what basically it says is, you can define the unit cell by, okay, excuse me, if I move the mouse, they'll be able to see the cursor, is it? Or do I need the pencil? No. Okay, fine. So you can define your unit cell this way also, because if you repeat this, you'll be able to recreate the pattern of the red ball and blue ball. You can choose it at this way also, where your red balls are at the corner, because this will also recreate your three-dimensional structure. You can draw it this way also. Okay, so what is the criteria? Can I choose any small cell and call it my unit cell? No. Of course, it should have minimum volume. It should be the smallest unit that is possible for that structure. But side by side, in that smallest volume also, it should be able to represent maximum symmetry of the cell. Like all the symmetry elements that are supposed to be present in your crystal structure should be present in your unit cell. Only then you can call it unit cell. So what are the two things that characterize? Minimum volume, maximum symmetry. Okay. And then how do we define unit cell? Because if I'm talking of unit cell, there should be some way, we say this, we define the unit by color, shape, size. So how do I define my unit cell? So there are basically 6 parameters, which are called unit cell parameters. And they are any object we can define along the 3 axes. So 3 parameters A, B, and C, which define the length of your unit cell along X, Y, and Z axis. Other than that, what is the angle between your A and B, B and C, and C and A, also known as alpha, beta, and gamma. The angle opposite to A axis, that is between B and C, is called alpha. Opposite to B axis between C and A is called beta. And the one opposite to C is called gamma. Okay, so the 6 parameters that define your unit cell are A, B, C, alpha, beta, and gamma. Moving forward, we also, okay, so what we'll do is the first initial slides, we are trying to understand the terms which as a materials chemist you are expected to know. Or whenever you read about it, you come across it, and then when you read it, it should immediately click to you what it actually means. So we talk about 7 crystal systems. What are crystal systems? So basically, crystal systems are nothing. And one thing that I would request you from now on is, whenever you read about the technical term, just try to understand what is the physical meaning behind that technical term. That way you will not forget it ever, and it will be more clear to you. The concept behind that will be more clear to you. So all of us, when we are taught crystal system, we simply remember there are 7 crystal systems. But what is that? They are actually 7 independent unit cell shapes that are possible in 3 dimensions. So only 7 unit cell shapes are possible, and hence you have 7 crystal systems. Now, one more thing I would like to add. Whenever we read, we say there are 7 crystal systems. The cubic has 4C3 axis. Now, again, a concept that I would like to change today is, so we do not say that the cubic unit cell has got 4C3 axis. It is the other way around. The presence of 4C3 axis makes a cubic unit cell. Okay. So that means shapes do not define the unit cell. The presence of symmetry element decides the shape of unit cell. Just to make it clear, now how does a C3 axis exist in a cube? Let me see if I have, okay, it is here. So just look at this cube, okay? Assume this is cubic. It has all A is equal to B is equal to C, alpha, beta, gamma are 90. Now by convention, why would this happen? A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90. Will happen if your 3-dimensional body has got 4C3 axis. Now I'll pause here for a minute, and for those of you who have not read it or not aware of it, what is a C3 axis? Okay. Now any axis of rotation, if you look at, so it is any axis that pass through a 3-dimensional body, and if you rotate along that axis, then what is the angle of rotation, that how many times do you need to rotate it to go back to your original shape? that number of times is your subscript on C. I'll just make it more clear. In other way, you can say that suppose along a particular axis, you rotate it by an angle, and then 360 divided by that particular angle is L, CL. For example, look at this second figure here. This is a cube and axis passes through it. I call it C4. Why? Because if you rotate it by 90 degrees, you will get the same cube. So 360 by 90 is 4. Okay. So this is C4. Now similarly, what is a C3 axis? If you simply can imagine the dice that you play your Ludo with. Okay. And now imagine an axis passing through its body diagonal. Just tilt your dice like this. Axis that passes through its body diagonal, the one that joins the farthest two corners. Now, if you rotate 120 degree along it, okay, so what will happen is your this corner will go to this corner and this corner will come to this corner. So you have rotated by 120 degree and you have got the, no, sorry, this corner will not go to this, it will go to the one at the back, which you are not able to see. Okay, so rotation by 120 degree brings it to the similar configuration. 360 by 120 is 3. So there is a C3 axis passing through the body diagonal of the cube. Now, how many body diagonals do we have? In a cube, we have 8 corners. Okay, so if you imagine joining those 8 corners, there are 4 axes. So there are 4 C3 axes. Now, if a material has to possess 4 C3 axes, automatically it will make its A is equal to B is equal to C and alpha is equal to beta is equal to gamma is equal to 90 degree. Okay? So that is what I wanted to emphasize here, that 7 crystal systems are defined by 7 sets of symmetry elements. And because those set of symmetry elements are present, that lead to that particular shape, which we call as cubic or tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. So these are the 7 independent unit cell shapes which are possible. And these are the criteria. So till now, you were actually studying that cubic has got this criteria, tetragonal has this criteria, and that is why this symmetry element exists. No, it is because cubic has these essential symmetry elements, so these criteria exist. Okay, so that was the first thing I wanted to tell you. These things would be available to you in the recording, and they are widely available in the literature. So you would know, you can read them later on. These are simply the facts that I stated here. Okay. Again, this slide shows the 7 unit cell shapes and how their parameters actually vary. So I'll only let me just discuss, maybe to make it more interesting. So cube, all of us know, that's a dice that we play in the Ludo. What is tetragonal? You make 2 sides equal and make the third side unequal, and all angles are still 90 degrees. That is my tetragon. What is orthorhombic? It's a shoebox. All of you have seen the shoebox, right? All the angles are 90, but A is not equal to B, the 3 sides are not equal. That is nothing but your orthorhombic shape. Now, that orthorhombic shoebox, what you do is you put a hand on the top face of the shoebox and then slide it, keeping the bottom face fixed, slide it towards any side, right or left. The shape that you will now get is monoclinic, where your A is, all the 3 sides are not equal, they are not equal in orthorhombic. 2 angles are 90, but because now you have slit the first top face, one of the angle is now non-equal to 90. Rhombohedral and hexagonal are the special cases where one of the angle is 120 degree. Triclinic is the simplest system in the sense A is not equal to B, is not equal to C, alpha is not equal to beta, is not equal to gamma, and none of them is equal to 90 degree. So triclinic has got no symmetry element as such. Okay. Now talking about another interesting concept, which is lattice. What is lattice? We talk about lattice a lot, right? Lattice is nothing but three-dimensional array of points that can represent your structure. Simple. For example, and I'll again repeat, lattice is the three-dimensional array. Array is nothing but arrangement of points to represent your crystal structure, to represent the repetitiveness of the atoms and ions in your crystal structure. And these points are called lattice points. For example, see this NaCl, NaCl and all, okay? Now, if you see that each lattice point is either Na or Cl. Now, there's one more interesting thing that I would want to tell you, it is not necessary that your lattice point will always have an atom or ion on it. No, it can be any point and still it can represent the 3D periodicity. I'll come back to it. For example, if I make this as the unit cell, let's say, joining these four Na, okay, now this is my 3D periodicity. Now suppose, and this is my lattice point, Na was lattice point. Suppose I put a point in between Na and Cl, and I draw a line from here to here. Go back and then I again go in between these NaCl and these NaCl. I will still repeat the three-dimensional. I'll be able to represent my 3D periodicity, right? So the take-home point from this particular slide is that your lattice point need not necessarily, most of the time, they coincide with your atoms, ions, or molecule representing the crystal structure. But they need not necessarily do so. Okay. Second point, if you join your points like you have done in B, where each atom lies at the corner and there is nothing in the center, these are called primitive lattice. Okay. However, if you decide to join your points in such a way where there is some lattice point in the center, these are called centered lattices. Okay. I'll repeat it once again. When you have only lattice points present at the corner, it is called primitive lattice. When you have lattice point present in the center as well, they are called centered lattices. Why are they important? We'll come back to it in a little while. What is a basis? Okay, we talked about lattice. Okay, and we talked about how the lattice point can create the 3D periodicity. And I just told you that your lattice point need not coincide with an atom or ion or the molecule. I might also add that your lattice point could be a group of atoms. It need not be a single atom. So what is a base? That group of atom or the single atom or basically no atom, simply a point. So what is that is called basis. So how we define basis as a crystal structure is defined as lattice with bases attached to each lattice point. I'll just explain it a little more, that will make it more clear. Suppose you want to create this crystal structure, this arrangement of flower. Okay. Now, if you represent each flower by these dots, and then you put flower on these dots, you will be able to recreate this structure. So this is your lattice because it is defining the site which needs to be repeated. And this is the unit which is repeated. Okay, this is your basis. This is your lattice. Basis plus lattice form the crystal structure. Second example. This is the point, lattice point. This is your basis. If you combine these two, you get this crystal structure or the structure that you want to make out of it. So repeating it again, a crystal is defined as a lattice with a basis attached to each lattice side. Or in other words, your lattice plus basis can recreate your crystal structure. Again repeating it, your basis could be a single atom, a single ion, or a group of ions, or a molecule. Okay? So example of crystalline solid that can be explained as lattice plus bases are NaCl, CaCl, and we'll talk about these structure as we move forward in this lecture. So I hope these were very, very basic things. I hope these are clear. I'll take a 2 minutes or maybe a minute's break and type any question if you have in the chat box. Okay, so I'll be live, I'll be online, but if there is any query, you may please type in the chat box. Please see if there is any question. Any questions? Anything that you would want to put? Okay. Sorry, the question is the final structure here are two layers of same lattice but different bases. Maybe if you can write what here, by here, what do you mean? Which slide are you referring to?
The final slide that we had viewed, the crystal structure there, the one with the black and red atoms.
Okay, so basically those simple black dots were your lattice. Okay, that is how you want to 3D periodically recreate your structure. But that black ball with the red dot is the basis that you need to put on those lattice point to make your crystal structure. Is that clear now? Okay, it is like this. It is like this.
Okay.
Sorry.
In there, you had written bases atoms. So I thought those are two different atoms, the blue, the black, and the red kind, and these are two alternating layers.
No, it's not alternating layer. I've only shown you, let's say, okay, how else I can represent it. Suppose you want to create a cube of, okay, very hypothetical, but let's say a cube of big globes, okay? Like this entire room, you want to make a cube of big globes. But where would you put the globe? Okay, now that depends on you. We have not come to that point, but there are various ways. You have simple cubate, you have face centered and body centered, and so on. So, let's say a teacher has asked you to make a cube of globe. Now, you want to know small blue globes. Where do I put my globe by? Then, what she will do is, like our nursery teacher would give us the homework, now she'll put the dots. Okay, here and here you put the globes. So that here and here, whatever she has marked is nothing but your lattice. That here and those points are your lattice point. And that globe is the basis. So when you actually put the globe on all the dots, which are the lattice point, you are able to recreate what your teacher wanted. Okay, is that clear now? So the dots were the lattice, they were the direction to you to put your things there. Whatever you are putting is the basis. And when you combine the lattice and basis, you get the crystal structure. Is that clear now?
Yes.
Okay, nice. So we'll go back to the lecture because we have only 15 minutes and I would want to finish some more. Okay? Fine. Okay, I'm not able to change the slide. Okay, yeah, fine. So, how many different, we studied there are 7 crystal systems. So, how many different lattice types do we have? There are 4 lattice types. The first one is simple cubate, where your lattice points are at the corner of the cube. Okay. Then you have something which is called base centered cubate. Now, in addition to the 8 corners, you have two opposite face lattice point on two opposite faces. They could be along the C axis, they could be along the B axis, and they could be along the A axis. But one pair of opposite faces is centered. Third is body centered, where you have lattice point at the corner of the cube and one lattice point in the body center. And the fourth one is face centered, wherein you have one lattice point at the corner of the cube And all the 6 faces, all of us know that a cube has 6 faces. All the 6 faces also have one lattice point. So there are 4 types of lattices. The simple cubic denoted by P, base centered. It is also called side centered. Somewhere you will also read end centered. So there are various names. It is denoted by C or A or B, capital, depending on which opposite pair of faces is centered. Body centered is denoted by I and face centered is denoted by L. Okay. Now, another important thing, because we'll eventually move to the crystal structure and there you will have to do all this. How do we count the lattice point? Most of you who already have done some sort of course in solid state chemistry would know that a primitive lattice, that is the one where the lattice points are present only on the corner of the unit cell, has ultimately got only one lattice point. And how? Because this unit cell will ultimately be 3D repeating itself, right? So each corner, if you can imagine, is actually shared between 8 cubes. Okay, let's say if I'm concentrating on this cube, then one on the top, then one on the side, one on the top of this side, one in the front, one on here, one there and there. So basically this corner is shared between 8 cubes. So ultimately one corner is contributing only 1 by 8 to this cube. Okay, and how many corners are there? 8. So 1 by 8 into 8. That means a primitive lattice has got one lattice point per unit cell. What about body centered? Now the one lattice point that is lying at the center of the unit cell is not going anywhere, right? It is contributing only to that particular cube. So in all, you have 2 lattice points per unit cell. One is contributed by 8 corners and one is contributed by the one which is lying at the body center. The face centered, now each lattice point that is put on a face, that is lying on the face of the cube, it should be easy for you to imagine that each face is actually shared between 2 cubes. So the lattice point that is lying on the face is contributing to 2 cubes. That means to 1 cube, it is contributing half. Okay, you can imagine a ball lying on a wall and that ball is shared between 2 rooms. So that is only half in 1 room. Okay, so and how many faces are there? 6 faces. 6 into 1 by 2, 3. So FCC lattice, face-centered lattice, has got 4 lattice points, 1 from the 8 corners and 3 from the faces. What about the side-centered? I have not drawn it here, but again, side-centered, easy to imagine. 1 comes from the corner and only 1 pair of faces are having the lattice point. Now 2 and each lattice point contribute half. 2 into 1 by 2, that is 1. So an end-centered or a side-centered lattice has got 2 lattice points per unit cell. Okay, I hope this is clear. Another term that I want to discuss with you is Bravais lattices. What are Bravais lattices? Now this is one term that you would encounter very, very frequently whenever you will study any literature or book talking about materials chemistry. Okay. Now Bravais lattices are the combination of unit cell shapes, that is your 7 crystal system and lattice type. They are formed by the combination, because ultimately how will you get your crystal structure? Na? You have to have a unit cell shape and you have to have a lattice, right? So you have to combine it. That is how you will get crystal structure. So Bravais lattices are the combination of unit cell shape and lattice type. Now, if we consider it logically, there are 7 crystal systems, that is 7 unit cell shape and 4 lattice type. That is what we studied in previous slide. So there should be how many? 28 Bravais lattices, 7 into 4. But there are only 14 Bravais lattices, not 28. And why? We'll look at it now. Why do we have only half the number of Bravais lattices that is possible, even though there are 28 possible? I'll just attend to your query in a while. Okay. Why? Because some of the combinations, out of these 28 combinations, now when we say that I want to decide a unit cell for my structure, on the very first slide I told you that a unit cell should have minimum volume or maximum symmetry. Minimum volume and maximum symmetry, not all. Okay. So what happens is the rest of the 14 combination which are not feasible means we don't consider them because ultimately they can be converted to a unit cell. That combination can be converted to a unit cell where it is possible to get either a smaller unit cell or the one with the higher symmetry. So you negate that. I know it's difficult to understand, but I'll give you one example. Okay. Now consider this. This is a simple tetragonal unit cell, right? Now a tetragonal lattice actually has got only two Bravais lattice, either simple or body center. Why not face center? Okay, now let us see why not face center tetragonal. Okay, so this is a simple tetragonal. Let me make a face center tetragonal. So I put lattice point on all the 6 faces. Now, if you look at it now, assuming the sizes were here A, B, and C. Okay, and A and B were equal, and C is the longer side. Now, if you join two such face center tetragonal cells side by side, like here, you can see that you can actually create another tetragonal cell here. You will say, okay, what's the problem? I can create it. But now how the situation changes is the diagonal of this face center tetragonal, if this side is A and this is A, this is root 2A. Okay. If this is root 2A, half of this will be root 2A by 2, that is A by root 2. Now, if you are able to make a tetragonal cell like this, it has the side A by root 2, which is smaller than A. That means I can actually have a tetragonal cell having smaller volume, and that can also 3D periodic recreate this particular structure only. But now my tetragonal cell is not face center tetragonal, it is rather a body center tetragonal. Now this is also tetragonal because this is A by root 2, this is A by root 2, and the longer side is still C, and this face that lies at the center has got lattice point. So now we have a body center tetragonal. That means if ever you want to create a face center tetragonal, you do not really need it because that can be represented by a smaller volume body center tetragonal units. Okay, that is the reason, even though 28 combinations are possible, only 14 are valid because the rest of the 14 can be represented in terms of the 14 that we have chosen with either the smaller unit, smaller volume or higher symmetry. Similarly, if you look here, the cubic is supposed to have a simple Bravais lattice, a face center Bravais lattice, and a body center Bravais lattice, but it does not have end center. Why? Let's say you have an end-centered cubic. Going by the same logic, now you take two such unit cells and join this. So what you get is actually a simple tetragon. So I can represent an end-centered cubic by simple tetragonal, and simple is a higher symmetry lattice than the end-centered lattice. So smaller volume, higher symmetry. That is why I will choose this simple tetragonal over the end-centered cubic. That explains why out of 28 combinations, only 14 exist as viable Bravais lattices. Okay. This slide only contains the summary of how the 14 Bravais lattices are distributed over 7 crystal systems. There is only one in monoclinic, one in rhombohedral, one triclinic and hexagonal, and orthorhombic has got all 4 types of lattices. Simple, body-centered, base-centered, and face-centered. Okay. Again, this I have kind of, if you want to see, you can go visit this slide later on, and you can, it'll be nice to see what 14 different Bravais lattices are there and what are their parameters. Okay. Now, what is an important condition for Bravais lattices? This is a necessary condition. The arrangement of the lattice point around any lattice point in the Bravais lattice should be similar. Now, what I want to say is that if you look at this kind of arrangement, let's say this is your 3D periodic arrangement. Let's say you're standing here, okay? So the surrounding around you is similar. You have these atoms around you. If you're standing here, the surrounding is still similar. So wherever you go, you'll be able to see the same surroundings. All the points have same surrounding. However, if you come to this figure, now this is the honeycomb lattice. Okay, this is the graphene. If those of you who know what graphene is, it is single layer graphite. This is the crystal. This is how the carbons are arranged in graphite. Now, this is a hexagonal lattice, but this is not Bravais lattice. Why? Because let's say if you are standing at point P, you have one bond going in front of you and two at the back. And the same is with point Q. One bond in the front and two at the back. However, if you stand at R, there are two in front and one at the back. So even though all the carbons are similar, but the arrangement around all the lattice point is not similar. Okay, so the area of point that is observed from P and Q is actually 180 degree rotated from what you observe at R. Hence, this is a hexagonal lattice, but this is not a Bravais lattice. For a Bravais lattice, the arrangement of lattice point at any point of the lattice should be similar. Okay, so sorry. So since we have already reached to the end, I will not start this concept because it will take some time. I would rather take one or two questions, and then you are, very welcome to send the questions either in the mail or to HBNI office, and then they can forward me the question. So maybe we'll move to the chat box now to see what your queries are. Okay. Choosing primitive cell, one criteria is maximum, right? And there should be a lot of various type how to figure out. Okay, so normally when we talk of symmetry, we say that simple cubic has highest symmetry, and your body center and face end center have got lesser symmetry. Okay, you'll study about these symmetry concepts as we move on in the course. Okay, and choosing primitive unit cell, if you are talking of Bravais lattice, maximum symmetry and half the volume. If you are talking of that example that I discussed, the end-centered cubic converting to primitive. So there the major criteria was halving of the volume. Okay, when you can define the unit cell with half the volume, you would not go with the one with the higher volume. All right, not exactly half, but A by B2. Yes. Any other thing? Any other questions? You're welcome to ask it later. Next class. Also, you're most welcome to compile your question and send to HBNI office. And I'll receive them and I'll try my best to answer them before your next class if possible. Otherwise, in max 2 to 3 days. Madam? Sorry?
Why not FCC tetragonal is there?
FCC tetragonal, because in FCC tetragonal, what you can do is if you join these, let's say this was my face, which has a center, if I join this, okay. Now in FCC tetragonal, this side is A, this is A, so diagonal is root 2A, Pythagoras theorem, okay. Now if I make this cell, इसका A जितना हो गया, this is root 2A by 2, A by root 2. Now you are getting a tetragonal cell where your side is A by root 2. In the earlier tetragonal, it was A. Now you're getting a smaller volume unit cell. Okay. Anything else? If not, then it was very pleasant having you all on board for the first lecture. In the next lecture, we'll try to finish the crystal structures and maybe discuss a little bit about what are the factors that affect the crystal structure. If at any point you feel some point is not understandable to you, I try to clear it at that moment only.
Thank you, ma'am. I have one question. May I ask?
Yeah, of course, please.
Good evening, ma'am. Ma'am,
You're not audible. Can you please check your mic?
ma'am, am I audible now?
Yeah, better.
Ma'am, you showed in one slide that some common axis of rotation. There you showed that A3 bar, C3 and comma 3 bar. That part, ma'am, can you please explain what does that mean?
Okay, so don't go about that. I was only trying to explain the symmetry element, which is axis of rotation. Okay, so axis of rotation, I'm sorry. Okay, how do I define the axis of rotation? Okay, it is any axis that passes through your solid. Here I would say unit cell. And along that axis, if you move it through the certain angle so that the shape remains same, you go back to the similar shape or the similar situation. And by how that CN, the end subscript, whether 1, 2, 3, 4 is decided is, that depends upon the angle that you have rotated it by. 360 divided by that angle gives you the value of n. Okay, for example, you consider because I cannot see you face to face, I'll only ask you to imagine, consider the dice with which you play the Ludo. Okay, now imagine you have a stick that passes through the top face of the dice, the center of it, and then it comes out through the bottom face. Okay, now on the top you have a square face. If you rotate, let's say you hold that stick and rotate it by 90 degrees, your dice would be similar, right? You cannot identify it from the original position. It will still be the square on the top. The dice, because once you have rotated it by 90 degrees. Okay. Now 360 by 90 is 4. So we say that this cube here, of course, this is not, I'll not go into symmetry elements because that's too detailed. But what I'm trying to say is that this stick is actually the C4 axis of rotation. 360 by 94. When you rotate it by 90 degree along this axis, it remains similar. Okay. Now a cube also has a C2 axis of rotation. How? If along the same axis, you rotate it by 180 degree, your cube will still look same. Now 360 by 180 is 2. So it has C2 axis of symmetry. But the most important criteria is presence of a C3 axis in the cube. Now, where does that C3 axis lie? The C2, as I told you, lied along the one that passes through the top face and the bottom face. Now, what you do is you take your cube, if you can imagine it, and hold it from one of its corners. If you hold it from one of the corner, on the other hand also you will have the opposite most corner, which is nothing but the body diagonal of the cube. Okay. Now, along that body diagonal, if you rotate by 120 degree, you will get the same shape. Okay, you will come back to the same shape. 360 by 120 is 3. So this body diagonal is called the C3 axis of rotation. Okay, now this actually elements of symmetry does not really fall under the purview of this course, but I'm happy to explain it further if there is any doubt. But you need to, use a little bit of your imagination to do this. Okay, are we good? Hello.
Thank you, ma'am. Yes,
Okay.
ma'am. Thank you.
Okay.
One thing, just then you are giving that, ma'am, that bar sign. Bar sign means that
Okay, so
opposite
we will
axis.
not go about that bar sign. We'll talk about it later on. Let's start with the simpler things. Okay.
Okay. Thank you, ma'am.
Okay.
Thank
Thank
you.
you so much. Yeah. Okay, then we'll wind it up here. And I would be very happy to meet you on Wednesday at 2:30. Okay. And I request all of you to join within 5 minutes so that there is no discontinuity in the lecture. And of course, the course coordinator mentioned that if you join later than 5 minutes, 15 minutes, your attendance for that particular lecture will be marked. Okay. So all of you have a good day and I'll see you on Wednesday. Thank you very much.